AQA A Level Physics for the electronics option, and this video is about sequential logic. So sequential logic is when the output is a function of time, so the signal changes with time. So it's not just static inputs and outputs as in the last video. This is where things actually are moving along, streams of bits, streams of digital information. And the important building blocks of these systems, we're going to talk about counters, a few different types of counter, usually base 2, although you can get them to count in any base. And then astables are very important. In any computer system, you need to make sure that all the different components are doing things together. They are all synchronized, and that's controlled by something called a clock signal. And the clock signal, which is like the conductor, waving the baton, is the astable, making sure that everything happens at the right time, the clock signal. Let's talk a little bit about counting first. Now, counting in denary, which is base 10, hopefully you can do that. You've got your ones and your tens and your hundreds and your thousands. So you've got in this 2361, you've got 1 1, you've got 6 tens, you've got 3 hundreds, you've got 2 thousands. The 1 is the least significant digit, and then the 2 is the most significant digit. Now, counting in binary, which is base 2, so this 1101, you've got ones and then twos and then fours and then eights and then 16s and 32s and 64s, etc., etc. Okay, so 1101, so that's a 1 and a 4 and an 8. So in base 10, that would be 13. So 1101 would be 13. The 1 on the right is the least significant bit because it's only ones. So LSB, least significant bit. The one on the left is the most significant bit because in this case that's the 8s. Okay, so this is our first counter, an n-bit counter chip. N-bit because it might be 4-bit, it might be 8-bit, it might be 16-bit. So it's a counter chip. It counts, and it counts in binary. Yes. Now, one thing looking at it, we've got 4 outputs. In this particular case, it says n, so you can have however many outputs it is. But if we had 4 outputs, Q0, Q1, Q2, Q3, the least significant bit is on the left. Yeah, remember that. The least significant bit is on the left. The most significant bit is on the right. And that's the opposite to what I said before, isn't it? Apparently, it's to do with having the least significant bit next to the clock signal. So we have our clock input coming from some kind of an astable. We have our outputs, Q0, Q1, Q2, and Q3, if it's a 4-bit counter. Enable here, that just turns it on and off. There's a reset here to reset the whole thing to get it started counting from 0 again. We can also get it to count up or down. So that's this input here, tells it whether to count up or down. So this is a counter chip. This timing diagram shows us how the outputs change as a function of time. This is just a 3-bit counter, so Q0, Q1 and Q2. Now, one thing to notice is that things happen when the clock pulse is on a rising edge. So there's a rising edge and Q0 switches, yes, from a 0 to a 1. There's a rising edge and Q0 switches from a 1 to a 0. There's the next rising edge and Q0 switches. There's the next rising edge and Q0 switches. Okay, so things happen when the clock pulse is on a rising edge. Looking at Q1, There you go. That's where Q1 switches, and that's where Q1 switches. Looking at Q2, that's where it switches. Okay. This 3-bit counter will count up to 111, and after that it goes back to 000. Notice the relationship between the frequencies of the clock pulse and the outputs. So the frequency is halving every time. As you go from the clock pulse to Q0 to Q1 to Q2, the frequency halves every time. One type of counter is a BCD counter, binary coded decimal. And basically all it does is it counts up to 9 in binary. Yeah, so it counts up to 9 in denary, which is 1001 in binary, and then it goes back to 0 again. So you should actually be able to count up to 9 in binary. And this is very useful for driving these things. This is a 7-segment display, and you should have seen loads and loads of these, you know, on like digital ammeters and voltmeters and power supplies and, you know, digital clocks and things. Obviously the signal, the binary signal, goes to something called a decoder, and then the decoder will drive the different LCD or LED displays for the 7-segment display. Then if we stack them in sequence, we can have ones, okay, and then when Q3 there's actually goes up to 1, then there's the carry bit. This C0 here is a carry bit, and the carry bit acts as a clock signal for the next counter, and so the next counter starts when you get to 10. And then similarly, the next counter starts when you get to 100, okay? But then the frequency, as we said, will actually be 10 times less, okay? So the ones will be counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The tens will be counting 1, 2, 3, etc. And then the hundreds will be counting 10 times slower than that. So this carry bit acts as the clock signal for the next unit in the chain, yeah, for the next decimal digit. This is called a Johnson counter, and this Johnson counter has got 10 inputs, and they basically produce pulses in sequence if you look at the timing diagram. So from Q0 all the way down to Q9, they take turns producing a short pulse. Okay, one use for it is for controlling a sequence of events, and hopefully you can recognize this. So my outputs Q0, Q1, Q2, Q3 take it producing a pulse in turn, and then these pulses, by using OR gates, I can control the amount of time. Look, there's my red light. Yes, then there's red and amber, then there's a green light, and then the amber, and then back to red, etc. for different amounts of time, depending on how many of these outputs I'm ORing together. Yes? And then the speed at which this all happens is controlled by a clock signal, and we can change the frequency of the clock signal in different ways. When we look at Astables, you'll see how we can do that. Now, in a digital system, it's important that different devices are coordinated. They are synchronized. So there is a conductor for the orchestra, making sure that all the instruments are doing the right thing at the right time. And that's what the clock signal does. And the clock signal is basically a stream of pulses, noughts and ones, produced by an astable multi-vibrator. Okay. A very, very useful chip is the 555. I remember when I taught electronics, it would get through loads of 741s and 555s. And the 555 with a joined together with at least one capacitor and a couple of resistors makes a jolly good astable. It's an integrated circuit, lots of transistors and things inside, and you can use it as a pulse generator. Very cheap, very flexible. It was used for years and years and years, but now there's more versatile, cleverer, more reliable ones. But nevertheless, that's a 555. This is a clock pulse here. There are various parameters that you need to know. So this is my voltage against time, if you like, ones and zeros. We've got the on time, the time that we're producing a one. We call that a mark, so that's M. The off time is a space. In this particular example, on my diagram, the on time and the off time are the same, but that's not necessarily the case at all. It doesn't have to be. So you've got marks and spaces, you've got T on, you've got T off. The period is the time for one cycle, so that's just T on plus T off. Then the frequency is 1 over the period, so that's the PRF, the pulse repetition frequency. So that will be 1 over TP. The mark to space ratio is M over S, so T on over T off. And again, on my diagram, that's 1 to 1, but again, it doesn't have to be at all. And then the duty cycle is basically the percentage of the time that it's on. So T on divided by T on plus T off times 100%. So you need to know these terms, yes, learn what they mean. A Schmitt trigger. This is clever. You can use a Schmitt trigger as an astable. And it's basically a comparator, and it looks at the value of the input. And if the value of the input goes over a certain value, then it switches on, but then it stays on. And it stays on until the value of the input goes below a different value. So there are two thresholds. There's the upper threshold and the lower threshold. Yes, if you look at this, if V in goes above the upper threshold, which is there, then it switches on and the output is equal to the supply voltage, Vs. But then if it goes below the lower threshold, which is there, then it switches on. So even if it goes below the upper threshold, nothing happens until it goes below the lower threshold. And we say that what we've done is we've introduced hysteresis. Hysteresis is where something lags behind the thing that causes it. Yeah, that's hysteresis. So when V in goes above the upper threshold, the output switches to Vs, but it does not, excuse me, does not switch back until V in goes below the lower threshold. A very, very good way of getting rid of noise. If you've got a digital signal which has picked up noise, look at the input and look at the output. Now, if we combine my Schmitt trigger with an RC circuit, yes, a resistor and a capacitor, then we can actually produce an astable, yes? And basically the time it takes for the pulses, my pulse repetition frequency, depends on how long it takes the capacitor to charge up. Yes, if you look at this diagram, my capacitor is charging. You should recognize the curve there for the capacitor charging. And when the voltage across the capacitor reaches the upper threshold, then all of a sudden the output, because you've got a feedback loop, so the output will switch to 0, so the capacitor discharges, and then it will discharge until the voltage across the capacitor reaches the lower threshold. Then the Schmitt trigger switches again and the output goes to the supply voltage and the capacitor charges again, and the result is that we produce these pulses which we use as a clock signal. And the frequency will depend on the value of RC, the time constant for the RC circuit. Notice that the not element, by the way, so when the input goes big, then the output goes down. When the input's down, then the output goes big. So the output is inverted, which it wasn't on the previous slide, which we have this here. So there's the Schmitt trigger followed by a NOT gate.